when we're looking at the next property of our vectors, right, we've got the position, we've got the displacement vectors. Those are, I suppose in some sense, like two types of vectors, position and displacement vectors. Yeah. But going back to the original way we defined vectors, right, we defined them as having magnitude and direction. Okay, and so as long as they have the same magnitude and direction, then they're the same type of vector. So really, we're interested in finding the magnitude and direction. Okay, so looking at this one, how can we find the magnitude of this kind of vector? How do we find its length? I mean, I can look at it and be like, okay, it looks like that long. It's like 1.5 of my hand span, right? But how do you find its length? Right, so it's actually just kind of using Pythagoras' theorem. Yeah? Because as you can see, if we do a bit of tricky rearranging, oh no, I'm frozen. You didn't see my animation? Hey, okay, cool. Man, seriously, too much investment. You can see that, yeah, it just resembles your right-angled triangle, and you can apply, really, a glorified Pythagoras theorem to the situation. Yeah? So you can go ahead and write that down. Now, one thing that you might notice is that we have to be pretty pedantic about the notation that we use, right? What notation have we used for vectors? We've used like, so there should be columns here, I'm not sure why this. We've used like this column notation, we've used this tilde notation, we've said like from O to A. But this here, trying to interpret, like have a look at what's going on here, right? When we talked about like magnitude and absolute values, right, we kind of use these two bars here, so they're kind of the same thing, right? The magnitude and absolute value, we can kind of treat them the same thing. They're like the distance from one point to another, or just a singular value. But what's this A over here? What type of quantity is this? Sorry? Well, the operation that we're applying is an absolute value, right? But we've talked about different quantities. What type of quantity does A need to be here?
Oh, is it plus minus?
Sorry?
Is it like plus minus because you square root?
Well, but I'm thinking about length, right? So I'm thinking about length. It kind of has to be negative. It kind of has to be positive, right? Yeah. That's a part of it. That's a part of it. Yeah, again, kind of similar ideas. The modulus, the absolute value, the distance, right? But this quantity here, right, what is A referring to? Like, what is A? The vector, okay. So this actually has to be a vector quantity, right? So you notice that there's no tilde underneath here. And this is just because of another notation that they often use, and I kind of tend to stay away from it. It's actually bolded. It's actually very difficult to tell, but a typeset that they use is they bold the font, and then that can be treated as a vector. Obviously, that's very difficult to do when you're writing. You can't control B and do a vector. Maybe you can like write over it a few times. Like, I don't know. There you go. Yeah, so that's why I'm letting you know that there's different types of notation here. Obviously, the tilde is a lot easier for you to write. But it's important to note that, as Carl was saying, this has to be a positive amount, right? Because we're talking about a magnitude, talking about a distance. But this here, it has to be a vector quantity because you're taking the magnitude of the vector. You're talking how long it is. It's not just a value that we're making positive, right? So that's the magnitude of vector. So far, so good. Now, direction becomes a little bit trickier now because although we can find out the direction of this, right? If I'm thinking about the angle that I want, it's measured anti-clockwise, right? I'm thinking about the angle here. Kyle, what kind of tools can I use here? If I'm thinking about the angle, and if I do this, I might go, hey, where's my 3 dots? Why am I missing dots? That, go away. That's spoiled, that's spoiled. I don't think you saw that. How can I find the angle here, Kyle? What do you reckon? Add the dots in manually. Yeah, right. We can just use right angle. This is again right angle trig, right? It's just going back to year 9-10 stuff, right? We can think about, hey, all right, what's the angle that I'm creating here? Okay, I'm thinking, yeah, I want to find theta, so I can use inverse tan of y on x. But I don't write a formula for the direction. I have to think about why. Let's say I had this vector. And if I apply this same idea here, and I did inverse tan of y on x, would that work? Would that give me the direction? No, why not? Well, what am I looking for, right? So the direction of a vector, right, I'm looking for, as you said, the big angle, yeah? So So I'm looking for this value for theta right now, because if I found inverse tan of y and x, I'd just be getting this small value here, right? So really, don't treat the direction as a formulaic situation. Always draw the diagram. Always think about how do we find it that way, okay? Because if you try and use inverse tan of y and x each time, then what you're going to end up with is you're not going to end up with the right angular value, because you're always going to be thinking about, hey, all right, what angle I'm actually looking for, and drawing that diagram will actually help you out a lot. Okay, so obviously those of you who've done complex numbers for finding the argument, similar kind of process. Only difference is that we're not going from negative pi to pi anymore. We're going from the standard 0 to 360 degrees there. So let's do a few problems on that. What do I need to do for magnitude direction?
Well, maybe draw it first.
Good. Draw a diagram. First step. Draw a picture. So what does that can look like? 5 across, 12 up. So I'll go up here somewhere. So that's our O to A. Right, and so magnitude, we can just apply Pythagoras' theorem there. Be careful with your notation, right? So I'm saying O to A, and I'm finding the magnitude of the absolute value, so to speak. And that's the square root of 5 squared plus 12 squared. And when you put that in, you should get 13. And then if I'm finding the angle here, I'm looking for theta, right? So in this situation, you can actually use, okay, well, tan theta is going to be equal to, be careful with this, 12 on 5. And so we can find theta using the inverse tan of 12 on 5. Right, because here's our vertical component, and there's your horizontal part. Yeah, so you're just using a right angle trig. Do you want to calculate that for me, Joel? Let's go nearest degree.
Well, it's 1 degree.
Show me.
In radians.
Okay, that's probably not it. Well, it's 1 radian. Okay, that's fair.
It's 1 radian.
Yeah.
It's 67 degrees.
67 degrees. Go, try the next one for me. If you want, there's a trickier one as well over the page. Question 5 is a bit different. Sorry?
How do you, we just find the magnitude?
Yeah. So this would be the magnitude, and you're representing that because you're writing the absolute value there. And as long as you say what theta is, that's the direction. So if you can write a concluding statement at the end of one, like magnitude is 13, direction is 67 degrees, if you want to be really clear. All right, who did I crack it to? You want to help me out, Angus? What'd you get? Yeah, more just cheeky extension 2 star. Magnitude, yeah. Same thing really, yeah. Sorry? Yeah. Yeah, so you just, I mean, also kind of, I mean, is that rounded or is that the... Yeah, so I mean, if you can, it's probably better to leave it an exact value. So, right, yeah. I mean, just because it just saves you, unless they specifically ask for rounding to correct several decimal places, just taking the Pythagoras theorem of those two lengths and then leaving it. Say square root of 58, was it? Yeah. I'm fine with that. I think that's good. And again, with direction, right? I think the best thing to do is make sure you're actually sketching this out properly, because just applying, tan theta is equal to the two values is not always going to get you the correct answer. So what are we dealing with here? We've got -3, -7. So looking something like this, and I still draw out like the components there because I want to see the right angle triangle there, right? So I'm looking for the direction here. So again, I'm going from this side of the x-axis, and I'm creating this anti-clockwise direction. I'm looking for that angle there, okay? What do I need to do here? So I'm looking for theta. So I can still find theta, right? But I just need to make sure what I need to do, an extra step that I do after I find theta. I had 180 degrees, right? Yeah. So theta is equal to, well, tan theta is equal to -7 on 3. Yeah, 7 on 3. Again, like I don't need to consider those negatives there because you can imagine just like flipping that triangle. I'm just looking for the angle that's there, right? So theta is equal to, what does that give me? Someone done that one? And 66 degrees, 48 minutes. So what you guys got? Yeah. And then, so but if I want the direction, like I said, we add 180 degrees to that. Okay, question 5. You want to have a go at question 5? Firstly, what's different about question 5? It's not the origin. It's a displacement vector. Good, using that terminology. So we're given that we want to find the magnitude direction of AB, given that, what do we have? OA and OB. Is that what we're given? Yeah. What was that, Emily? What OA and OB? What?
OA was 2, 1.
Yep.
And OB was 5, 4.
OB 5, 4. And this is the kind of situation where you're definitely thinking, hey, I really need a diagram here, right? Because when I'm looking at them, A, B, that's just starting and endpoints, right? So let's go ahead and construct OA and OB first, and then we can get a better idea what's going on. So OA, I'm going 2, 1, so 2 across, 1 up. So maybe something like this. Okay, 2, 1. And then OB is 5, 4. So 5 across, 4 up. So maybe somewhere here, maybe. Should be using a ruler for this, shouldn't I? 5, 4. How does that look? There you go. Yeah. Maybe I'll give myself a bit more space here. Let's use a different color as well. Okay. There you go. And what did you try, Angus? Okay, so the AB vector, we know what that's going to look like, right? It's going to look something like this. That would be AB. And then what do we do from there?
Well, I don't know if it's right, but I drew out the X and Y for AB.
Yeah, so kind of like you're constructing a right angle triangle?
Yeah.
Yeah, that's cool. And what is that?
It was the 3 was X and Y.
Yeah, so you're going from 2 to 5, you're going 3 across. And then from 1 to 4, you're going 3 up. Yeah, that's good. And there's your right angle triangle, right? So I guess the difference with the displacement vector is that now it's not as easy because you don't have these X and Y components, right? You need to try and interpret them yourself. Another way to do this, apart from visually, is you can kind of do it algebraically, right? It's actually kind of like distance formula if you think about it, right? Distance formula is literally the situation. What's the distance between 2 points? So if we want to write this out algebraically, we can do that. So AB and its magnitude, that would be the same as 5 minus 2 all squared plus 4 minus 1 all squared. Yeah, which is just 3 squared plus 3 squared. Is that square root 18? Yeah, sweet. Okay. Right, so a few different ways. If you're comfortable with the visual aspect, or if you're happy to just use distance formula, either of those are fine. Okay. And direction we can apply in the same way now, right? We have the horizontal and vertical components. So I think either way, you do need those horizontal and vertical components, right? And so we can work out again that tan theta. Again, realizing that it doesn't really matter where it's placed. Before we saw that, right? The direction of the vector doesn't depend on where it's on the Cartesian plane, right? It just depends on what these horizontal and vertical components are, yeah? So it'd just be 3 on 3, or tan theta equals to 1. Tan theta equals to 1? What's our exact values? Good. We haven't forgotten everything.
Sorry?
We haven't forgotten everything yet. No, I didn't. I mean, that works too.